All right, object is thrown straight upward. Which graph best represents the relationship between kinetic energy and the height of the object after its release point? So right now you're just comparing kinetic energy to height. All right, and we know that potential energy is mgh. And so we know the higher we get, well, the higher we get, our potential energy increases, okay? So as height increases, potential energy increases. Let's say we throw, there's a lot of kinetic energy at the bottom. As we throw upwards, our velocity is going to decrease. Why does our velocity decrease? Because your acceleration due to gravity is pulling that object down, right? And so your velocity is going to decrease as you get to the top. And at the top, your velocity is zero. And if your velocity at the top is zero, well, ke is 1/2 mv squared, and then, well, ke is also must be zero. Well, so you have a lot of potential energy at the top, and as your height increases, well, what happens to your kinetic energy? Well, your kinetic energy decreases because again, you have a lot of kinetic energy at the bottom because you it starts with velocity, and as you go up, well, your energy goes to zero. But as you go up, your height increases, and so your potential energy increases. So there's an inverse relationship here, right? So the lower the height, let's say you lower the height, and this is the height, and this is 0 to 10, and this is like at 10 as well. So at a height of 0, you have a lot of kinetic energy, right? Let's say it's 10 joules, and as you go down, as you go higher and higher, well, your kinetic energy starts decreasing. And so at a height of 10, you have no kinetic energy, but at a height of 0, you have a lot of kinetic energy. And so there's an inverse relationship, and so A would be the correct answer. Um, Why is it not curved? Mainly because KE, if we were to compare KE to PE, right? Well, there's no square in the formula for PE, or KE as well. So we can't really treat it like a squared. And so what this is saying is basically X is equal to Y, right? Or rather, hold on, it's 1 over X, 1 over X. I'm sorry, or something like that. The math is escaping me right now. Math is escaping me. Uh, but because it's not squared anywhere here at all, we can't make it a curve. Can't make it a curve. And there's no square in that formula. We're just comparing two numbers. Number two, 65 Newton weight. And so again, we know that weight is our force due to gravity. Falling from rest, so our initial velocity is 0. We know that acceleration is negative 9.8 meters per second squared. And we fall a vertical distance of 5.3 meters. And so now what's our kinetic energy? Well, we want to know what our kinetic energy is. After it has fallen this distance, what was our kinetic energy? Now, at the top, at the top, at the top, we know that our potential energy is something. So potential is mgh or fgh. That's what mg is. Fg is equal to mg, right? And so Fg is 65. Our height, right, there's a height of 5.3 meters. And so our potential energy is somewhere around 910, 915. Oh, no, not, I'm sorry, 340. Somewhere around there. And my kinetic energy at the top, right? Kinetic energy at the top is going to be 0. Well, why? Because kinetic energy is 1/2 mv squared. That's the formula. And so, well, if my velocity at the top is 0, well, then my kinetic energy is going to be 0 as well. Now, when the object has fallen to the ground, we know that my total energy at the top, which is what the conservation of energy says, well, my total energy at the top is going to equal to my total energy at the bottom, right? Bottom, top. So my total energy at the top must equal to my total energy at the bottom. And at the bottom, we have a height of 0, right? Our height at the bottom is 0. And if we know that P is mgh and our h is 0, well, then our potential energy is 0 as well. Well, what's our kinetic energy at the bottom then? Right? The conservation of energy says that my energy at the top must equal to my energy at the bottom. It must have went somewhere. The only place where the 340 joules of potential energy could have gone was the kinetic energy. And so your kinetic energy is 340 joules. And so that's your answer. Right? All the energy had to go somewhere and went into the kinetic energy of the cart. 3. A 0.5 kg kilo ball is thrown vertically upward with initial kinetic energy of 25 joules. Approximately how high would the ball go? Okay, so we know that as we go up, right, my total energy at the top must equal to my total energy at the bottom. At the bottom, my potential energy is 0 because my height is 0. And my kinetic energy at the bottom is 25 joules. All right, well, and at the top, how high would the ball rise? We know at the top, right, my velocity at the highest height, right, highest height is 0. And well, if my velocity at the highest height is 0, then my kinetic energy must also be 0. This is something we learn in projectile motion. At the highest height, your velocity is 0. And now, well, what's my potential energy? My potential energy is mgh, right? So all my kinetic energy at the bottom, if my kinetic energy at the top is 0, then all my kinetic energy at the bottom went into potential energy. So we can say that my potential energy at the top is 25 joules. All right, and so, well, now we can solve for h because that's what we want. So 25 is equal to mass. My mass is 0.5, right? And g is 9.8 because that's my acceleration due to gravity. It's a positive acceleration. And 25 is equal to 4.9. I'm around 4.9 to 5. And so 25 divided by 4.9 is going to give me a height of 5, around 5, right? Around 5. And so my answer is B, 5.1 meters. 4. A diagram below shows a moving 5 kg cart right at a hill at a height of 10 meters high. For the cart to reach the top of the hill, what is the minimum kinetic energy of the cart in the position shown? Okay, so what is my kinetic energy? Well, if we kind of look at this diagram, for you to get on top of the hill, your kinetic energy at the bottom of the hill must equal to your potential energy at the top of the hill. At least. At least. If you want your velocity at the top of the hill to be 0. You can have a higher kinetic energy. Let's solve for kinetic energy first. So we need a kinetic energy at the bottom that equals to my potential energy at the top, right? Because all my energy has to go somewhere. My potential energy at the bottom is 0. And so we want to know what kinetic energy is. And we know that potential energy is mgh, where mass is 5. 5. Just ignore the 0. Don't want to erase it. 5, 9.8. And our height is 10. So 10 times 10, I'm rounding this in the 10. 10 times 10 is 100. 100 times 5 is 500 joules. 500 joules. So we need a kinetic energy at the bottom to be 500 because all that kinetic energy has to go somewhere and must go to potential energy. I must transfer the potential energy, and so you have a kinetic energy here of 500 joules. And so the answer choice is D. Right? The answer choice is D. Now, let's say you have a higher kinetic energy than this. What's going to happen is that as it gets up to the hill, what's left over is going to be into the velocity. So it'll go at a high speed at the bottom, it slows down. And once it gets to the top, it'll still keep going because it still has kinetic energy. If it only takes 591 joules to get up here, and let's say you start with 520 joules, well, at the top, your potential energy is 491, and then your leftover kinetic energy is 29 joules. right? It's still moving, but at the top it has a higher potential energy. It's still moving, but it has higher potential. You can ignore that last part if you don't really care. Uh, it doesn't matter that much. 5. As the pendulum swings from A to B, its total mechanical energy does what? Again, we know that total mechanical energy is just the sum of all energies. Sum is sum of all energies. And so we know that your total energy, unless work is done on this system, well, it remains the same. And assuming no loss to the energy. Which statement is true about the swinging pendulum? Again, I showed you on this GIF, right? Showed you on the GIF. B, C, A. So up here you have a lot of potential energy, right? Let's say it's 10 joules. And you have no kinetic energy here because you didn't really release it yet. And at B, well, as it goes to B, well, all that potential energy turned into kinetic energy. So now you have kinetic energy of 10, right? And you have potential energy of 0. And the same thing here. And all your kinetic energy as it went to the top, your PE is now 10 joules and your KE is 0. So the answer, the potential energy at A is going to equal to your potential energy at C. So A is wrong, right? B is wrong. B is wrong as well because we know that there's no kinetic energy as A. C is wrong because we know these two potentials are not equal. And so the only thing that's true is D. So the correct answer is D. 7. And so we know that, well, if and going back on the diagram I drew earlier, 5.7.5 kg. Distance is 1.5 meters. And so, what's the total amount of kinetic energy mass? So we have to solve for potential energy at A. That's right. What's my potential energy at A? And then we can finally solve for kinetic energy at the bottom, right? So my potential energy is mgh 7.5, 9.8, h is 1.5. We'll round this 10, 10, 15, 15 times 8, 30, 120, somewhere around 120. It's probably like 110 joules. Now, my potential energy at A is 110 joules. And as it goes down here, all that potential energy turns into kinetic energy, right? This is the ball. So all my potential energy here turned into kinetic energy, so my kinetic energy is 110 joules. So the answer choice is C. C, C, C. That's conservation of energy.